Hello everybody, we have been discussing shift register. In this class, we shall consider certain application of shift register. So, these are the few things that we shall have a look. So, the first of all, what we see is as one application of shift register is parallel to serial conversion that we do through shift register that can be used for converting a parallel stream of data that is getting generated. For example, in some process say 8-bit data is generated, samples are generated which is encoded by 8 bits. So, that is generated, one sample means 8 bits are getting generated and it needs to be transmitted to some other place. Okay. So, one option is to have 8 transmission channels. Okay. So, that at the other side those 8 bits will be appropriately collected, but having those 8 wires or 8 channels is a bit costly. Okay. And if the data rate with which this is generated is such that we can make a parallel to serial conversion and quickly we can at a higher rate we can send it to the other side and there we can collect it and convert through a serial to parallel conversion, serial input to parallel output, that kind of shift register. Then we have a this data 8-bit data appropriately received at the other side. Okay. So, this is one thing that can reduce the cost of transmission by converting parallel data to serial and having a serial communication, okay, between transmitter and receiver. And of course, we need to have a appropriate protocol to find out start of the data message or the information and the stop of it, so that next 8 bits again appropriately be picked up. Okay. So, the issue here is trade-off is with the time, that the rate with which you generate and the rate with which you transfer is transfer rate need to be as many times more depending on number of bits that is getting converted. Clear? So, this is one thing that you can see on reduction of cost. So, parallel to serial and then serially it is pushed out, okay, through a shift register. Next, we can use shift register to introduce time delay and the input data stream somewhere here IC 7491 we have already seen. This is say B is the control input, okay. When we are keeping it at high, then whatever is the input at A, right. So, at that time when B is at low, okay, whatever is the input at A, we have to go by this truth table. So, whatever is the input at A, that is getting transferred to the output, okay, after 8 clock delay, right. So, that is IC 7491. We can have 4-bit shift register, then it will be after 4 clock delay. So, the same variation that you see over here, so that will also be available here, is not it, right. And this clock, the clock time period multiplied by number of flip-flop units that is there in the shift register will be giving you the total delay between this input and the output, and that will give you the time by which the binary data stream is getting delayed. Okay. So, if the clock is of time period is of 1 microsecond duration, then by this arrangement we will get 8 microsecond. If there are 4 flip-flops in the shift register, it will be 4 microsecond. So, and if the clock time period is say 2 microsecond, in this case it will be 16 microsecond delay. Is it clear? So, how you can have a clock generated which is of different time period? One convenient option is that of using IC 555. Okay. So, 555 timer is very much used, and this is in stable multi-vibrator mode, in which RA and RB, through RA and RB this capacitor gets charged, for which the charging time is 0.693 multiplied with RA plus RB, these resistance values and capacitance. Okay. And for discharge, discharge happens like this. So, discharging time is 0.693 multiplied by RB into C. So, total time period is like this. So, with appropriate choice of RA, RB and C, you can fix the T value, time period, and accordingly the delay can be introduced. Clear? Right. So, next we look at application of shift register in sequence generation. Okay. So, here we are thinking about that a particular sequence will be generated repetitively. Okay. So, there could be an application where we are looking at a particular pattern coming say 3 times or 4 times, which cannot be random. So, basically that serves as a pilot or a header of something else to follow. Okay. In a random message, somewhere a pattern like a particular pattern may come, but it is getting repeated number of times, it is unlikely, it is relatively unlikely. Okay. So, that could indicate that certain events are to follow just after that. Okay. So, there could be other applications as well for a sequence getting generated repetitively. So, for that we can think of a shift register, and a shift register like a 4-bit shift register over here, see it is loaded with 1011 okay, initially, and after the output of it is fed back to the input of it the way you see here. And if you now clock 8, then what will happen? This 1 will go out, right, this 1 is going out, and after that this 1 will come out, and this 1 is getting fed here. After that 0 will come out, and after again another clock 1 will come here, right. So, another clock, so this 1 will come up. So, this is the way it will keep circulating, and this pattern 1101 will keep getting generated. Is it okay? Instead of 4-bit, if we have got a 8-bit shift register, and say we have loaded it with a 100, 10, 110, right. So, again the output of it is fed back as input of this one. So, 0, 1, 1, 0, 1, 0, 0, 1, it is getting generated. So, one cycle is getting completed. So, another one will, the next cycle will start with another 0, and this particular pattern will get repeated. Okay. So, with 4-bit you can get 4-bit pattern, 8-bit, 8-bit pattern. Okay. But if you say in some case you are loading it with say 1011, again 1011. So, what will happen? Of course, 1011 will come in one cycle of 8 twice. So, basically you are generating a 4-bit pattern. Okay. So, if you appropriately load it, then you can get n-bit pattern out of a n-bit shift register the way we have configured it. Is it fine? So, that is what has been mentioned over here. Now comes sequence detection. There also shift register can be useful. Okay. So, by sequence detection, what we mean is that identifying a specific pattern from the incoming bit stream. Okay. So, here this is the serial data in the bit stream that is coming, okay, and which is made to go through a shift register. Okay. And this shift register is used for the pattern matching, sequence detection. Okay. And the sequence to be detected, we can store it in another register, right. So, for example, if we want to detect a pattern in the incoming stream 1011, we can store it over here in a register. Otherwise, we can connect it to VCC. For 0, we can connect it to ground, 1 again to VCC, and 1 to ground. So, that is hardware. Okay. But if you want to change the pattern that we want to detect, then again we have to physically disconnect and connect this VCC and ground. Alternative is to use a register like this. So, we can load the register with another 4-bit number, which will be detected for a different occasion if so required. Okay. So, that is the advantage of having a register in place of hardwiring the bit values that we want to detect. Okay. And here what is happening? So, look at a particular case, the outputs of this bits that are to be detected, they are made to go through a XNOR gate. Each of these are going through a XNOR gate. XNOR gate, at the output indicates equality of the input. So, if 0 0 and 1 1, then the output will be 1. Okay. XOR, if 0 1 and 1 0, the output will be 1. So, XNOR is just opposite of it. So, when the input is 0 0 and 1 1, then the output will be 1. So, that means it is actually giving the logic for equality, equal whether it is 0 0 or 1 1, in either case the output will be 1. Okay. And all these 4 bits, when they are equal, these AND gates output will be 1, indicating a match or detection of the specific sequence. Okay. So, the example, in this example, at this point of time 1 0 1 1 is to be compared, and we have got 0 1 1 1 in the incoming string, which is stored in this shift register. Okay. So, what we see, 1 and 1, this 1 and this 1, it is compared. So, it is generating 1, this 1 and this 1 compared. So, this is generating 1. Now, this 1 and this 0 will give you 0, this 0 and this 1 it will give you 0. So, this AND gate 1, okay, then this is 1, the rest 2 are 0. So, the output is 0. Next, what happens? This 1 gets in. Okay. So, what will be the modified values of this shift register, because it is getting shifted as a whole to the right. So, now this is 1, this is 0, this is 1 and this is 1, is not it? So, all these now XNOR gate having same equal values, 1 1 here, this 0 0 over here, 1 1 over here, 1 1. So, all of them will give you a output which is 1, and the AND gate output will be 1. So, that is the sequence is detected. Okay. So, that is the way we can make use of the shift register, where the incoming this bit stream will pass through a shift register. Okay. Next, we can see use of shift register, what is called getting ring counter. Okay. What is a counter? Counter keeps count of a particular event, in this case the clock trigger, in this particular example. Okay. But that event, that trigger can come from some other place also. So, when it reaches a specific number, we say the count of something has taken place. Okay. So, if we say counter which is giving a value, modulo value of 8, modulo 8. So, it is counting 8, and when the count of 8 is completed, an output is triggered. Okay. An output signal is made active. So, that is how the counter works. So, it keeps a count of the input that is triggering the circuit in certain manner, and internally the state change takes place in such a manner that it gets incremented, and when the count, a specific count has been achieved, an output is activated. Is it clear? So, that is what we understand as a counter circuit. More about counter we shall discuss next week. Okay. So, when we talk about this shift register as a counter, so we are using the shift register again in a feedback mode, and in this case, unlike the sequence generator where we are putting a specific sequence, we are putting in one example all of them are zeros and only one value is 1. Okay. So, this is how we are starting, and then when, so that when one, so this is the case over here. So, this is 1 and all these values are 0, and then with one clock trigger is getting now counted here, as I said. So, what will happen, this 1 will come over here. So, this is the 1, right, and rest of the values will be 0. So, this 0 is pushed here, this 0 is pushed here, and this 1 is getting in, it is becoming 1. So, that is what you can see, that rest of the values are 0, 1, this is 0, all of them are 0. One more clock, what will happen? So, this one will come over here, that is what we know as shift register operation, we have discussed it in the previous classes. Okay. So, next time this one will come here, right. Next time, next clock this one will come here, and after 8 clock, okay, you will see that this one is again appearing over here, isn't it. So, if you have connected an LED or some output action and all, so from this point another time when it is getting getting a high input, okay, and say the LED is glowing, then you can very well say that 8 clock trigger has taken place in between. So, a count of 8 has been completed, clear, and this can be achieved by any shift register with 8 such flip flop like 74164 you can take, and then the feedback can be taken, and from that you can achieve the way we have achieved a mod 8 counter. Okay. So, in this case the flip flop output directly, the last flip flop output, the way you have seen it itself indicates the count of 8 has taken place, right. So, if we have instead of this one, right, say 0 0 0 1 and 0 0 0 1 initially, then what will be the count by this particular shift register? So, 1 is coming here, again 1 will come here after 4 clock pulses, right. So, it will be a mod 4 counter, right. But with this ring counter arrangement, as many number of flip flops, okay, if it is n bit shift register, maximum we can get a mod 8 mod n count. Okay. So, that is what is mentioned, okay. But we can get less, depending on how we are initializing the flip flop, clear. Next, we look at another type of feedback by which what we get is called Johnson counter. Okay. So, in Johnson counter, this is the flip flop, right, and this is the shift register. So, the output of it is inverted and sent as input to the first flip flop. Is it clear? So, serial data out is inverted and fed as input to the input of serial in input. Okay. Now, if the arrangement is such that shift register is such that inverted output is available at the serial out as serial out, then you do not need this extra inverter. So, that inverted output you can feed back, okay, as serial in. Okay. So, this is the making of it, because of which it is also called switch tail counter or twisted tail counter, right. Popular name is Johnson counter, but it is also called switch tail counter or twisted tail, because tail is twisted, I mean it is inverted, that is the meaning of it. Okay. Now, how this particular circuit works? So, if we initialize it with say 0 0 0 0, okay, then we take this example. So, this T prime is getting fed back as a serial in. Okay. So, 0 is coming here as 1, right. So, 1 will go as input and rest these 3 zeros will come here as these 3 zeros, clear. So, now it is 0. So, what will be coming as input? Serial in is 1. So, this 1 is coming here and this 1 is getting in. So, this 1 and these 2 zeros will be coming as these 2 zeros. Still it is 0. So, what will be fed back is 1. So, this 1 is coming here. So, 3 1s and this is 0. Again still it is T is 0. So, what is fed back is 1 T prime. So, this 1 is coming here and all 3 1s is following these 3 1s, this 3 1 is coming here as these 3 1s. So, 4 1s have become. After that what will happen? This 1 now fed back as 1 prime which is 0. So, 0 gets in, these are 3 ones, then 0 0 gets in, these are 2 ones, then 0 0 0 gets in, these are 1, and what next? This 1 will go back, so it is 0, so all 0. So this is all 0 means again it will get repeated. Is it fine? So what we see in this case, that we are getting it is getting repeated, the sequence state is getting repeated after 8 clock pulses. Okay. So it can give a count of 8 clock pulses, right, and this is a, in that sense, with 4 such flip flop, 4-bit shift register, we are getting a count of 8. So modulo number is 8. Okay. So that is the Johnson counter providing you. So with n-bit shift register, it can be extended. So if it is 5-bit shift register or 8-bit shift register, it will be 10 or 16 this count that can be achieved. Okay. Now, as I said, the external world needs to know that when that count of 8 or 10 or 16 has been completed, isn't it? So it is the internal states that are getting circulated, that are getting repeated after 8 clock pulses, as we have seen, but the outside world need to know, right. For that it need to be what is called decoded, and the states need to be decoded and made available to the outside world. Okay. So in ring counter we saw that no other external circuit is required. The output flip flop directly can be made available to the outside world, and whenever it goes high, that means count of 8 has taken place, isn't it? But in this case, if you consider a similar scenario, say t is 0, over here, it is 1, but it is remaining 1, again it will become 1 after 4 clock pulses. So if you only take it from t, it is not going to work. Similarly, from S, from R, from Q, if you try, okay, in none of the cases you can see that a modulo, a count of 8, okay, can be ensured. But what you can see, right, that if you take only say Q and T prime, right, Q prime and T prime, that means both of them are 0, that is occurring again over here, right. In between, in any of these states, it is not your 0 and 0, isn't it? So if we take a logic like this, and then is this output, it will become 1 once here, again over here, after a count of 8 has taken place, after 8 clock trigger has taken place. Is it clear? Okay. It is possible to have all these 4, that means Q prime, R prime, S prime, T prime, right, but that will require a 4 input gate. So that is a more complex circuit. We are talking about the minimal requirement. So earlier no external gate is required, here we need a gate with that is 2 input logic gate. Okay. And we can see, other than this Q and T prime, you can have other combination also. So for example, this 1 0, okay, Q is 1 and R is 0. So this is again occurring over here. So once it occurs, right, it will again occur after 8 clock pulses. So that could also be a decoding logic. Is it clear? So decoding logic for Johnson counter, as we have seen, in this case requires a 2 input logic gate. Now interestingly, you can work out, it is for 4-bit shift register, you can work out for 5-bit shift register, 8-bit shift register, any other. And for Johnson counter, you will see that every case what you would be requiring only a 2 input logic gate. Okay. More than that is not required. More than that is not required. Okay. With a 2 input logic gate, even for 5 bit or 8 bit shift register working in Johnson counter mode, okay, giving you modulo 10, 16 or whatever, I mean depending on that number, twice the shift register size, okay, a 2 input logic gate is sufficient for decoding. Okay. So, this is the way we can see that it works, and you can think of other kind of initialization also, and we can see that it progresses in this manner. Okay. So, with this we come to the conclusion of this class. What we have seen is that parallel to serial conversion at transmitter end and serial to parallel conversion at receiver end help in reducing number of transmission channels, and shift register comes useful there, because after parallel to serial conversion then the data is made serially out, and there lies its utility. And we also saw that serial data can be appropriately delayed by selection of clock period and also the size of the shift register used. Okay. If n bit shift register and t is clock of t time period is used, then nt is the delay in this case. With serial data out fed back directly as serial data in, n bit shift register can generate up to n bit long pattern repetitively. So, there you can use shift register as sequence generator, and shift register can be used as sequence detector also to identify a specific pattern in the incoming bit stream, okay, where we are doing a bit by bit comparison. XNOR gate is used and XNOR gate outputs are put to a multi input AND gate, and that AND gate output is when it goes high, that means the pattern is detected. Okay. And n bit shift register in ring counter configuration can act as a modulo n counter, and in Johnson counter configuration as modulo 2 n counter. And for ring counter configuration, we do not need any decoding logic, extra decoding logic, but for Johnson counter we need 2 input logic gate for decoding purpose. Okay. Thank you.